Good afternoon, everyone. Thank you for the introduction, Sophie. As Sophie said, I'm at the University of Leeds. I'm in the Centre for Doctoral Training of Complex Particulates, Products and Processes. And I study unwanted nucleation and accelerating it and inhibiting it. And what I'm going to talk to you today is an acceleration method, so accelerating the nucleation of slow nucleating systems. So a background to my research focuses on two questions, really. So, do we always want crystals? And as I said, the answer to this, when we've got unwanted nucleation, is no. There are quite a lot of products out there, if you think in food, in pharma, in fuels, in agrochemicals, where we don't want crystals to appear in the products. And also, how can we limit or stop unwanted crystallization from occurring? And this comes from potentially knowing when it might occur and then taking steps to avoid it. So background to this accelerated testing procedure I'm going to talk about. So nucleation kinetics, as we all know, very well studied, but we can get quite slow transformations. If we take a product such as ritonavir, so this was an antiretroviral HIV drug that went to market, but 2 years later, it underwent a nucleation event and had to be taken off the market because it was no longer effective. So that took 2 years for that to occur. We also have products containing additives, such as diesel fuels, where they add additives, spend millions, billions on creating additives to stop wax nucleating in there. But if we have conditions such as these here, where we've got it's cold for a long period of time, how effective are these additives? How long will they be able to inhibit this nucleation from occurring? So something that's used as an industry standard to test what might happen over long time periods is accelerated predictive testing. And if you think of something like a thermal stability test, we might have a product that's held at an elevated temperature for a short period of time, and then an Arrhenius relationship is used to extrapolate back to how the product might react at room temperature over an extended period of time. So we really need an equivalent for crystallization for that. And given that supersaturation is a driving force for a nucleation process, in order to achieve accelerated nucleation, we need high solution supersaturations. But importantly, in achieving high solution supersaturations, we have to be able to do the extrapolation to low supersaturation conditions, so we can predict what might happen at these conditions. So realistically, we know that it's important to understand and determine accurate nucleation kinetics at high supersaturations in order that we might have this accelerated predictive testing. So if we look at a traditional method in which we can determine nucleation kinetics, we can use something like classical nucleation theory. And we can do the standard isothermal method, where we might use the temperature jump method here, which a lot of you probably know. We have a solution that's held at an undersaturated state. We then rapidly cool to a set supersaturation. And after that set supersaturation is achieved, we wait until crystallization occurs, and this gives us our induction time, our time lag to which nucleation occurs. And it works on the principle that the supersaturation is inversely proportional to this induction time, which in itself is inversely proportional to the rate of nucleation. Now, through classical nucleation theory assessment, we can determine crystallization parameters such as the effective interfacial tension, the critical radius size, the number of molecules within this critical nuclei. So we can determine key parameters from it. And we can determine this quite easily experimentally if we take a piece of kit such as the Technobis Crystal 16, which is what I've used for the work I'm going to present, where we've got 16 reactor wells. We have 4 independent heating blocks, and it just uses transmission data to provide information about crystallization and dissolution temperatures. So if we take a model system such as paraminobenzoic acid, so if we look at it here, it's a nice model to use. It's got 3 distinct functional groups. It's a good model pharmaceutical compound, for instance, and we use very common solvents, ethanol and water. Using this temperature jump method, we can get data such as this. So for ethanol and for water, over different concentrations, we can alter the supersaturation, we can determine induction times, and we can determine these parameters that I talked about earlier. Now, unfortunately, using this method, we're limited to the supersaturations that we can achieve. So you might notice that these supersaturation levels are relatively low. And what this means is our induction times are quite long. So there's not much of a difference between these induction times. If you think if we've got a product that might take months to crystallize, we need to be able to extrapolate back to a period of hours or minutes, something that's experimentally capable in a lab setup. We can get quick data from. What you'll also notice is that because of low supersaturations, we have very high standard deviations of the data. So this is an issue with this temperature jump method, in that it's just because nucleation is stochastic and you've got a low driving force to nucleation, standard deviations can be quite high. So the time at which it takes, this induction time, can range dramatically for the same system under the same conditions. And this has led to the use of probability distribution functions to determine accurate information from induction times. But it is quite a high throughput experimental method. You need at least 80 repeats to get accurate data about the probability. So using this temperature jump kinetic analysis, we see that we can get kinetic information from this, but we're not actually able to achieve our high supersaturations that we would need for accelerated predictive testing. So we need another method. So what I'm going to introduce to you now is a method I developed called isothermal by design. And unlike this temperature jump method, it works through anti-solvent crystallization, where an anti-solvent is added instantly to a system to achieve rapid high supersaturations. And it's quite a simple procedure. At the minute, all you need to do this is a temperature controlled vessel, a syringe and a needle, very, very basic lab equipment. And through this, developed a workflow for standardized testing. So you can use this with different systems using this isothermal by design procedure. I'm not going to talk you through this workflow. It's available in literature published on this, which I'll present at the end. And I'm going to talk you through some of the steps today, but it is there for standardized use. So getting isothermal by design using the same system, a PABA, using ethanol and water again, but this time a mixture, and we're using water also as an anti-solvent. So in order to do this, you have to understand the solubility over the range of compositions from in this case, ethanol all the way to water, and select your composition based on this. So I selected a composition of 70 to 30 weight % ethanol to water. And this is because for this system, you get a hump in increasing solubility with small additions of water. So picking this composition ensured that in adding more water, I only actually ever increased supersaturation, and so could accelerate and lower induction times. Simply choosing a saturation concentration and a range of temperatures to get a large overview of the system. Now, again, very simple method in order to just achieve different supersaturations. Oh, sorry. All I did was change the initial amount of solution I would put into these crystal 16 vials. So I always made them up to 1 mil, but I would select a different initial solution volume. So I might put 4 mil in, 0.4 mil in initially, and then add 0.6 mil of water to make up to 1 mil. In the same manner, if I had 0.7 mil to start with a solution, I'd add 0.3 mil of water in. And this ensured that my solutions stayed the same volume each time and that different supersaturations were generated. I did this for each temperature. Now, one thing that isn't taken into account all that often when doing anti-solvent crystallizations is that when you mix an anti-solvent into a solution, you get an enthalpy of mixing. So in my isothermal by design method, what I'm going to introduce is calorimetric calibrations to counteract this enthalpy of mixing. And this is where this isothermal by design concept comes into. So for each initial solution volume, I added the anti-solvent in at different temperatures. Simply in this manner here, I would have a solution at a set volume, add in my anti-solvent, which was a given temperature, and use a temperature probe to measure the change in temperature caused after this addition. And I could record this by this temperature probe, and I could make a plot over this range used to extrapolate to a delta T of 0, whereby we have a true isothermal anti-solvent method. And as you can see from this, we get data like we see here. So in this figure, what we have is solutions that are held at 297 Kelvin, so 24 degrees Celsius. And each color represents a different initial solution volume. And all I did simply was select different initial anti-solvent temperatures and then add my anti-solvent in and record the temperatures. So what you'll notice here, for instance, if we take this value here, from an extrapolation, we know that in order to maintain a solution at 297 Kelvin, we have to offset our anti-solvent temperature by about 20 degrees. So this enthalpy of mixing is huge. It's not a small effect shown here, and we get a range of effects depending on the starting initial solution volume, but it is linear and it's quite easy to extrapolate. And in doing this, we can get a total view of our system over a range of solution temperatures, such as this figure here, where for a given temperature, we know the required anti-solvent temperature that we need for a given initial solution volume to create this isothermal process, to stop the enthalpy of mixing occurring, in a sense, to counteract its effect and to ensure that we're getting accurate isothermal information. So to take from this, we know that anti-solvent temperatures must be offset when performing anti-solvent crystallization procedures isothermally, because it has such a large effect on the system. And if we want accurate data for predictive testing, we need to take it into account. So the next stage was simply just to perform the experiments. And this was using these calorimetric calibrations I've just shown to ensure that temperature was maintained isothermally, and to use a range of temperatures and solution volumes to get this large overview of the system with large range of supersaturations. And experiments performed quite easily using the Crystal 16, different blocks, different ones had solution in, different temperature control block had our anti-solvent in, and again, simply using a syringe and a needle, extracted the anti-solvent and then put it instantly into the solution, and then waited a period of time till crystals were detected, and this was the induction time. So working on the same method of the temperature jump analysis, but this time with anti-solvent. So the data collected from this, if we look at this figure here to the right, we see that supersaturation versus induction time. From the low supersaturations I used, we're getting induction times in the order of 10,000 seconds. But as we increase this, we actually find that supersaturations at the higher level reduce induction times to around a second. Now I should point out, I was able to achieve higher supersaturations than what's shown here. It's just induction times were so fast, it just wasn't detectable. So if we had a system that might take months to crystallize, it shows that we can extrapolate quite a long way to potentially a more experimentally lab-based useful time frame. So overall, the reduction in induction times was around 4 orders of magnitude, and that's great if we want our accelerated testing capabilities. What's also very nice is you'll notice that results fall on one single curve. So we're talking about extrapolating from high to low supersaturations. This is great. It's showing supersaturation dominates, and it's creating this linked system throughout. Also, standard deviations were reduced dramatically at high supersaturations. So they followed the same sort of trend. So low supersaturation, we had high standard deviations, as I discussed previously for the temperature jump method. But as we increase supersaturation and we increase the driving force to nucleation, we're able to get more reproducibility. And this is great for extrapolations, because it means our data at the high supersaturations is quite accurate, and it provides more accurate potential extrapolations. We also can get more accurate kinetic information by this method than by using anti-solvent method that doesn't take into account this enthalpy of mixing. So if you look at the figure here, the red data is from isothermal by design, the black is from a traditional anti-solvent method that doesn't take into account enthalpy of mixing. And you can see for the exact same system, we get different data. This is to do with this temperature effect. And what you'll also notice, the IBD results have much lower standard deviations, again, because we're more controlled in the system. And we get, realistically, what this means is we're getting more accurate data from isothermal by design than if we didn't take into account this enthalpy of mixing. What's more, we get, because we've got so much data and we're using so many different compositions, etc., we get a great overview of the system. And from an analysis of this, looking at changes over a single temperature range, we spotted two separate regions, which might suggest that at the low supersaturations, we're getting heterogeneous nucleation. But at high supersaturations, we're getting a shift as the driving force increases to homogeneous nucleation. We can also determine our parameters from this in the same manner as a temperature jump, where we can use classical nucleation theory. And we can get a table such as this, where we get quite a lot of data from our system. We get a range of concentrations, a range of compositions over the range of temperature studies. We can still get our parameters such as the effective interfacial tensions and the critical cluster sizes and the number of molecules within them. We also obviously study a far higher range of supersaturations. And potentially this data is maybe a bit more accurate than you might expect for the temperature jump method at these high supersaturation ranges. So overall, IBD, we achieved significant reductions in induction times, reduced variability in results at higher supersaturations. We had a greater accuracy in induction times and hence kinetic information compared to a traditional anti-solvent method. Enabled a large overview of the system to be gained and determined a nucleation mechanism change. And this again shows great applicability towards accelerated nucleation testing. And maybe more than that, just high supersaturation environments. If we think of complex drugs that are made nowadays that need high supersaturations, potentially methods like this can be used to gain good kinetic data for it. So in conclusion, looked at nucleation kinetics of a model system of PABA in ethanol and water through two methods. Both isothermal, but one was the temperature jump method, one was IBD. The temperature jump method unfortunately limited the solution supersaturations that are achievable, and so aren't suitable for accelerated testing. But this new method, IBD, could achieve these high supersaturations. Importantly, and if this is anything you take from this talk, anyone who performs anti-solvent crystallizations, you have to take into effect this enthalpy of mixing, because it has quite a large effect. Therefore, you need to calibrate your system and make sure that the data you're getting at the end is accurate kinetic information. IBD enabled kinetic parameters to be determined in the same manner as temperature jump, and lowered induction time significantly, which is key for potential extrapolation to low supersaturation for accelerated testing. And through its use, developed a workflow for more standardized testing to aid future work with using methods such as this. So I'd like to thank EPSRC, my CDT at Leeds, Infinium and Syngenta, who are two of my industrial sponsors on my PhD project. I'd also like to thank everyone for listening. I'd like to highlight that these two articles here relate to this work. So if you're interested, please have a look at them. My email address is below as well if you want to correspond, and if you've got any questions, that would be great. Thank you.
Thanks so much, Peter. Eleanor, I think we've had one question in the chat box already, but everyone do enter your questions for Peter and we'll come around to as many as we can.
Yes, please try to put more questions. Peter, there is one already, so that's related to your IBD methodology. Charlie from Bristol is asking, so if you're adding water to produce supersaturation, but you might produce more stable hydrates. Have you thought about this? Is there, how can you somehow mitigate this risk?
Yeah, no, it's a good point, and it's system dependent. So for this system, there weren't any hydrates formed from this in the solvents used, but depending on your system, you might potentially form hydrates. Again, that's not necessarily a bad thing, because maybe you're in a formulation, for instance, where you might have unwanted hydrate formation, and it might allow you to gain kinetic information from that. But it is very system dependent. It's the same in terms of polymorphism. You could also potentially see this as a good way to screen potential metastable polymorphs, but also you might get this instability of polymorphs and want to detect that. So it's very system dependent.
But would you be able to check that you form a hydrate when you plot your curves without necessarily do an XOD? So would you see like a discontinuous
potentially,
behavior?
yeah. Like I said, I couldn't say 100% because I've not seen that, but you might expect the kinetics to be slightly different, I guess, and you might see a discontinuity in some of the analysis results.
Okay, thank you, Pete. Zarin Ansari is asking how the enthalpy of mixing affect the induction times, and they also ask whether when you talk about supersaturation, if it's absolute or relative.
Yes, it's absolute. So it's the ratio of concentration to saturated concentration. So it's the S value instead of relative. But yeah, in terms of the enthalpy of mixing, how it affects induction times. If you think you're trying to analyze something at 20 degrees Celsius, for instance, if you add an anti-solvent and it increases the temperature to 24 degrees Celsius, the data you collect isn't what you think it is. And realistically, if you're in a reactor setup where you've got it to set to maintain at 20 degrees Celsius, as soon as the temperature increases, it will work its way back down in a non-linear way to that temperature. And because induction times are stochastic, that means each one of your induction times will be taken at a different temperature. So you can't really analyze the results against each other. You couldn't repeat a result. It's not potentially accurate. And this leads to the this data here, which is a comparison of the black being where the enthalpy of mixing isn't taken into account and the red where it is taken into account, and you get different data.
Okay, thank you. I think Zarin made more of a statement than a question, but that they enjoyed, but it was good to repeat anyway. Alex from CCDC is saying, you mentioned a lot about extrapolating from the current result. Is this something that, well, you did say a little bit already, is this something that is also system specific? How versatile do you think this workflow is?
Yeah, it's a good question, Alex. So I've been doing this on a completely contrasting system, whereby this is a very aqueous PABA water ethanol. I've been doing the same for icosane, so an alkane, toluene and acetone, and we get similar trends occurring. It seems to be, as I showed with this, we're changing quite a lot in the system, but our supersaturation is kind of dominating what's going on. So we kind of see these trends of kind of a potential extrapolation. One thing that does need to be taken into account, though, as I mentioned a bit later on, is this here where we're potentially getting two mechanisms. Again, this is system dependent, but obviously if you're extrapolating on a curve, you don't want to be mixing these parameters. You want to stay in one of these sections. So you need to take that into account if it occurs in the system you're studying, but which is why it's good to get this large overview. But yeah, good question.
Yeah. What did you use as a solvent and anti-solvent for the other system that you mentioned? They are waxes, right?
Oh, yeah, toluene as a standard solvent and acetone as an anti.
Sia is asking, so she's saying, if the solvent temperature is crucial for the anti-solvent crystallization, do you think whether it is the same in the case of the initial heated solution temperature? Oh, I'm not sure I understand it.
No, I'm not sure I understand the question.
Sia, if you want, you can open your microphone and clarify this.
Okay, I mean, if it is the cooling crystallization from the single solvent, do you think if the temperature, the initial temperature of the solution will be important, will be affect the induction time of the crystallization? I mean, if the supersaturation is the same, it's have the clear solution, but you use the like 60 degrees Celsius, and another sample is 80 degrees Celsius, but it's the same concentration. Do you think it will affect the induction time? Yeah.
Yeah, I think temperature does affect it, because if you think of, like you say, kinetic mobility within the solution, over small ranges, it wouldn't have that much of an effect, but over quite a large range, anyway, your initial solution temperature will affect it. Yeah, definitely.
Thank you.
Thank you, Sia. Thank you both. A question, Jason from Bristol is asking, how much difference does it make if you use a different, how much difference does using a different anti-solvent make if you keep the supersaturation compensation consistent?
So a given supersaturation for different mixed solvents. Again,
Jason, if you have a microphone, feel free to speak, because I'm not sure I fully understand your question.
Just if you're looking at induction time as a function of supersaturation, if you change the anti-solvent so it's not water, but keep the supersaturation consistent at those numbers, how much difference does it make? Because as soon as you inject the anti-solvent, you're changing the system, right? And you're going to be changing what happens to the nucleation kinetic. So I was just wondering if you keep the supersaturation the same with a different anti-solvent, do you see the same curve?
It's a very good question, actually, that, and one in which I'm not 100% sure on. I would imagine when you get to the higher supersaturation, when the driving force is high enough, you get something quite similar, but it depends on the solubility differences. You know, we're calculating supersaturation based on the solubility known over the range of compositions. So changing the anti-solvent, you have to know the solubility over the full range, and so that might alter it, definitely. Interestingly, in the second publication I put right at the end, we go through analysing this data compared to like a pure solvent system, and you do find it extrapolates quite nicely from the mix to the pure. Quite interestingly, but you do get these changes in kinetic parameters and the thermodynamic parameters of rate expression. It's a good question. I hope that answers.
Yeah, thanks.
Thanks, Jason. Thank you both. Do we have time for a last question, Sophie?
I think Peter has another meeting he needs to run to as well, so it might be our speaker's time as well. But thank you so much, Peter and Eleanor, and everybody for your questions. Peter's email is on the screen there, so if you wanted to jot that down in the next minute or so, then I'm sure he'd welcome some more questions in the next few days if you'd like to email him or share those papers.
Yeah, great. Thank you, Sophie. Thank you, Elena.